So basically, this is a session meeting that we do every week and present a paper. For this week, I'll be presenting. My name is João, and the paper that I chose was narrow user embeddings from browsing events. I'm sharing my screen. So I'm sorry guys that I didn't share the Google Drive there, but I was making notes on my own sketchy app here. So can you guys read on the screen?
Yeah. Maybe zoom in just a little more. Yeah.
All right.
That's good.
Okay. Well, so basically the paper is the authors they are talking about how can we create implicit representations for users, or for actually, if we see to the data side, for if we can encode information about objects into embeddings in unsupervised ways, so that maybe we can because all right, let's start talking from the beginning. So basically the paper, the authors, they had a problem where they wanted to classify users that were browsing through the internet with their age and their gender based on their browsing history. All right. And by browsing history, I mean the pages that they visited, the queries they made on Google. So they wanted to use this information to see which would be the genders of those users, what was the age of those users. But the way they went for it was not to process the information directly. So as data accumulates, and I've written here, the creation of implicit representations for large amounts of data becomes very useful for us. Not only because we don't need to input all the information, the raw information, into our models, which is not always feasible, but also because those implicit representations then after they get created, they sometimes can be used in more than one model because they encode the information of the raw data. So basically what the authors propose is to use neural embeddings for this. And with embeddings, I know that we've been talking a lot about embeddings since Alain is doing some research with graphs embeddings. But they try to go for a different way of embedding. So basically this browsing history is a bunch of data, which is a bunch of rows of data related to a single user. And they want to create a vector of numbers. So it's simply this, a vector of numbers that can represent those characteristics in a n-dimensional space, so an arbitrary number of dimensions of numbers. And just, I know that maybe someone here is not acquainted with embeddings. I've put some examples here. So basically, one of the main uses of embeddings is in natural language processing. So a word can be represented with a vector of numbers that represents each one of the characteristics. Of course, normally those are way bigger vectors, and we don't know exactly what each one of the numbers in those vectors represent. But they basically try to plot a specific object in a multidimensional plane, and try to make the related objects to be close to each other. Right? So this is an embedding, just for remembering. All right. Why do this? Okay, so while behavior information and many other kinds of information that fit into this digital footprint that we have available nowadays in many cases. They may be very rich to create a profile of certain user, for example, but they are not easily implemented as features in models because they are large aggregates of data. Using them as raw data implies in a very computationally expensive work, and also a lot of other technical complexities. Okay. But normally, there are two ways of creating embeddings. We can create embeddings. So just to make it clear, when you create an embedding, you normally you initialize those embeddings randomly. So it's a random vector of numbers, and then you try to engrave the behavior of those objects that you see in data in those vectors. So it's basically through an objective function, uh, you update them just like you would with the weights of a dense layer in a neural network. We're updating them as you train the model. Okay, so now jumping to what I was saying before, there are two ways of creating those embeddings. Of course, there are maybe more ways, but you can create them through the usage of a supervised problem. So you have the labels, you have the problem, and then you run them through a neural network and try to make those vectors be representative of what they should be representing. So it is the vectors that you create have a direct relationship with the label. And in those cases, there is not much generability to those vectors that you are creating. It's not that they are encoding the information about the object, but about the object in relation to that label. And there is also the way that they did in this paper. Actually, they did both ways, but the point of the paper is what they did with unsupervised learning. So they created a separate problem where there were no labels, and they were just trying to encode the information from those browsing events into the user's embeddings, and also at the same time creating embeddings, so vectors of numbers for each one of the events. I hope I was clear until now, because now I'll be talking a little bit more about the problem in specifics. So just to make clear, like sometimes we skip those parts and it all seems like a piece of magic. Like they have 25,000 anonymous. They have the web browsing records of 25,000 anonymous users on Bing from February 1st of 2018 to July 31 of 2018. So that's a reasonable amount of data. So the average browsing events per user is 582. And what they call events in the context of the unsupervised learning, embeddings, and stuff is just the web page titles. So when we say that each one of the events has an embedding, we are saying that each one of the web page titles has a vector of numbers representing this web page title. And here there is a catch, because while they are trying to create those unsupervised embeddings that represent the whole data, the whole user, and that can be used across multiple problems as feature, they also append this unsupervised created embeddings with supervised ones. Okay, so this must be clear for us. They are using both types of embeddings and they are aggregating them. But when they compare the results, they show the results of only the supervised embeddings and the supervised embeddings plus the supervised embeddings. So how are they creating those supervised embeddings? They are using different data. So for the unsupervised embeddings, they are using the web page titles, and each one of them has an ID and a vector of numbers, right? And for the supervised embeddings, which are normally not problem specific, and even in this case, they have one set of embeddings for the gender problem and one set of embeddings for the age problem. They are using the queries that were generated by these users during this period of time. So the queries on Bing. And for those extra features, they have a train set of 20K of the users of the 25K. And their split is based on users. That's also important to notice. So there won't be obvious data leakage on this things. And the remaining ones go to the test set. 10% of the test set is used for validation, just standard stuff. All right. Okay. So are you guys like with me? Like, or am I going too slow, too fast? You know.
From okay.
Okay.
All right. I'll go for it. All right. They create, for the purpose of creating those unsupervised embeddings, so those vectors of numbers, they use two approaches. I'll go more deeply on the simplest approach here, but the other one is not that more complex too. We can talk about it later. Just for the sake of time, I went deeper on one of them. And it is the new ID. So they have the new ID and the new text. And what the new ID is that they create basically, as I said, a vector of numbers which are randomly initiated for each one of the events and for each one of the users. Okay, so then they create a matrix with all the user embeddings and with all the event embeddings. All right. After that, they, as I said, randomly initialize them. So they are both actually matrices with random values, but with a set number of dimensions based on the number of users, the number of events. And an important thing also to notice, so that in a way to demystify what is happening here, is that the number of dimensions in those vectors is 200, and it is just 200. Like they set it to 200. It could be 201 or 210. They just set it to 200, maybe because they test with another values, or maybe because it was an arbitrary choice. Okay. So how they do to tweak those vectors in order for them to represent the events and the users. They use a very simple approach. So what they actually do here is to create a framework where they define the percentage of the chance, the probability of a certain user performing a certain event as this equation here, which is actually, even though it looks very mathematical, it's pretty simple. Like they're multiplying one vector transposed by the other with an exponential, and then summing all the events on the bottom part. They're trying to get this percentage, and then the same thing, they are maximizing these probabilities. So for a given event and a user, they are trying basically to create vectors that represent the probability. Yeah. And also there's this. They are using negative sampling. So the final equation is actually not this, but as it was purely mathematical, the computational cost of the second part here, the divisor of the equation, is very high in the context of we're doing this operation with all users and all events. So they use negative sampling, which is a mathematical resource, to make this to approximate this function and get into a more feasible thing. But that's a detail. But they are basically creating a framework where they are trying to get the probability of a user performing a certain event. So it's always this, what they're trying to encode into these vectors is specifically this. What's the probability of this user doing this event given the vector of numbers of this user and the vector of numbers that represents this event? That's what they're doing. So this has no label. It is an unsupervised problem. And by doing this, they are not biasing the vectors, the embeddings creations. They are just encoding the information. That's very important. All right. So now that they've done this, they used this equation and maximized the likelihood of behavior of events on the basis of user and the event representations. They have those embeddings for all the users and all the events already completed. They are done. And here, what I said earlier applies. So at the same time that the paper focus was to create those unsupervised user embeddings, they are also creating supervised user embeddings. Through a supervised problem, here you can see, but the material they are using is the search queries. And here with the browsing data that we were talking about, where we have the web titles, and we are relating them with the users, is this blue thing here. Okay, so they are appending, concatenating both of those embeddings, and they are using that concatenation as the features and the only features to predict age and gender. So those two problems were not related with the objective function that we used to create unsupervised embeddings. They are trying to create general purpose representations of the user behavior. And now, the most interesting part is to show this, the results. So here you can see the models that we are using on this part here. So where those features, those embeddings, unsupervised and supervised, are being inputted. And here you can see without the unsupervised embeddings and with the unsupervised embeddings. So for every model, we had a huge jump in accuracy. And that's amazing. I mean, and the F score also jumped a lot in every single case. So they are adding new data. So if this data is relevant, it is expected for the accuracy and the F score to jump. But there is a catch, and I'll show you later. And for both problems too, this is very impressive. So for both problems, they got like, and just by the way, each one of those lines represents 10 runs of the model, and then they are using the mean here. And as I said, there were two models, the new ID, which had the process that I described, and the new text, which instead of using the IDs of the web titles, they used they encoded the text. They used basically NLP to create the embeddings. So they were processing the content of the semantic content of the web titles instead of just creating those embeddings out of the IDs. They were encoding the words in the web titles, basically. And here we can see that there's also a difference between the without. So they said that the new ID performed better for age, while the new text performed better for gender prediction, which is cool. But both of them had like significant improvements over the base approach, and both of them, when used together, were better, specifically in the age case, age prediction case. So that's cool and all. But here they compare this with distinct ways they could have solved this problem. So here, I think that you can see this graphs, right? But without the browsing data, they had a very low accuracy, a very low F1 score. And here, what they call merge and multi-view are ways of using this browsing data, which is the data that was only available before in our unsupervised embeddings. They are inputting this data directly. So they are inputting this data directly into the model. The first one, the merge, they are concatenating the browsing events that we saw, the web titles, with the search queries. And the second one, which is the multi-view, they are creating two distinct embeddings, two distinct supervised embeddings, and they are using so one of them for the search queries and one of them for the web titles. And you can see that the new approach, which is their approach with the unsupervised created embeddings, they perform better in both tasks. Of course, in the gender prediction, it seemed that it was very close, specifically the F1 score, but they performed like way better in the age prediction. And the most interesting thing is the predicting time. So the amount of time that it takes to predict. And here they just like went straight over the roof with a way lower time. This is also interesting because, as I said, Alan is working with network embeddings. Here they show the comparison between this unsupervised way of seeing things, and it's very cool to see that this approach they used is also very in line, if not better, than the network embeddings. So yeah, like talking about the paper, that's basically it. I don't know if I went too fast or too slow, but this was the paper. We could talk more about the new text if you guys want, but it's a very straightforward way of creating those embeddings. So do you guys have any commentaries about the paper or any mistakes I made? Do you want to comment?
I would be interested, like, with this type of research. I mean, how does it usually work with, like, how people get the data? I mean, are they, for example, working for Microsoft or very closely that they get this Bing data, or how does it work?
Yeah, I think that they actually had to request it because they in the paper they specifically what's the word for this?
They were working for Microsoft at the time of the research, right? This was their internship project.
Yeah, but this is also like they had to not compliment. Agradeceram.
Acknowledged.
They acknowledge the data provider. It's not very easy to get those informations, but they were anonymous, right? So they of course were not identifying who the users were. But the way to get this information is directly straight from the source. definitely. Yeah, I think I will stop sharing the screen.
I think a cool takeaway from this is that this is, especially the new ID, it's a technique that could be applied to any pairs of two different entities. So, for instance, a card holders and merchants. So we could learn joint embeddings for these two entities that would encode the probability of types of users having transactions at a certain type of merchant. Or you could encode card holders and MCCs. And I think this is something that there presents some potential for applications, right? I'm sure you were thinking about this when you read the paper too. Like we could think about ways of capturing these pairs of entities and trying to learn the encodings for them, and then we could use these learned embeddings for a bunch of other problems, right? As features for other problems. But I think also the problem they formulated to learn these embeddings, which is the probability of this user and event happening as a pair. I think this is something that we could use also. Like if we learned embeddings that encode the probability of a cardholder having a transaction at a certain MCC, then at transaction time we could identify anomalies, like this user is not expected to do transactions at this type of merchant or this type of business, you know. So I think this presents an interesting technique for identifying these anomalous events.
Yeah, I completely agree. And like there are many ways that this can be applied. Like I went some time like thinking about this. We can go like even deviate from like we can use it as secondary things. Like for example, we can check for the check for the. I don't know if I should stop. Maybe I should stop the recording, right?